Hello and welcome to yet another session of statistical tutorials with RStudio. Today we will discuss about continuous random variables, a very important topic in the domain of engineering statistics. Almost every type of data which exists in the world of today can be modeled as continuous random variables. These data often show a definite pattern. It is essential to understand their inherent uncertainties. This is basically done by evaluating the probability density functions as well as the cumulative density functions. So let us have a look at the sections which we will be dealing with under this topic. Continuous random variables can be broadly classified as normal distributions, uniform distributions, lognormals, exponential, Weibull and Gumbel, etc. etc. First we'll look into what is a continuous random variable, the PDF, what the CDF means, the mean and the variance, and the continuous uniform distribution. Now these 5 topics will be covering the next 2 videos. So in today's video, I'll introduce you to the basics of continuous random variables and its understanding by visualizing certain real-life problems. But before that, let's do a brief recap. I already discussed about random variable in broader sense, which is a variable whose possible outcomes are a result of a random experiment. Now depending on type of outcome, the random variables can be either a discrete or a continuous random variables. Now, the discrete random variables are those where the outcomes are finite and distinct, which I have already studied in my previous video. However, in continuous random variables, the outcomes are infinite within an interval, and the integral of its corresponding probabilities over a range must be equal to 1. Here, the summation of discrete is replaced by integral since the variable is continuous. Hence, it can be represented by area under a curve. A continuous random variable can be effectively modeled by a CDF, which is also called as a cumulative density function, whose derivative is in fact the probability density function. A simple example can be the possible case of all possible numbers between 1 and 1000. We can start from 1, 1.002, 1.003. Now we can understand the possible number of outcomes will be close to infinity. Now let us have a look at more examples of continuous random variables since we'll be dealing with this today. The following lists certain continuous cases, the first being that of a vibration measurements, temperature, calibration, calibrating an instrument, etc. etc. I've stated the continuous random variables and its possible outcomes for each case as well. We can see the range of values is infinite for each case. So now we have a brief idea of what a continuous random variable is. But how is it represented? The answer lies in the understanding of its probability distribution called the probability density function or the PDF. The PDF of a continuous random variable is a smooth curve, a function of x denoted by the symbol f of x. Now since PDF is continuous, the probability of occurrence of a single value will be 0. The histogram is actually an approximation of the PDF. For each interval, the area of each bar is a proportion of the measurements in the interval. The proportion is the probability of occurrence of a measurement within that interval. Thus, the area under fx over an interval represents the probability that a measurement shall fall within that interval. Here we have the conditions for a probability density function. Each probability has to be greater than 0. The sum of all the probabilities must be equal to 1. As discussed before, the probability of a particular value will be 0 in a continuous distributions. Also, it will be 0 in an undefined interval. Now, fx is used to calculate an area that represents x assuming a value which will fall in the interval between a and b. So basically, it gives us the probability of x lying between a and b. So for continuous distributions also, there is no need to distinguish between inequalities. Further, the CDF or fx is given as follows, which calculates the total probability up to a value. So here the limit of the integral goes from minus infinity to x. Now as we have discussed before, the PDF is the derivative of the CDF. A continuous random variable is often defined as the one that has a continuous cumulative distribution function. So we can understand the importance of understanding a CDF. So friends, now let us solve a problem for better understanding. The question reads, let the continuous random variable x denote the current measurement in a thin copper wire in milliamperes. Assume that a range of x is from 0 to 20 milliamperes and also assume the fact that a probability density function is fx, which is equal to 0.05 for x belonging to the interval 0 and 20. Now, what is the probability that a current measurement is less than 10 milliamperes? So, we'll calculate the PDF first. So, fx is equal to 0.05 as already discussed. Thus, the probability that the current is less than 10 milliamperes is calculated using the formula with the interval going from 0 to 10. The answer is basically 0.5. This is represented by the colored area in the graph. Also, the probability for current lying between 5 and 20 is calculated, which comes down to around 0.75. Now, the CDF or the cumulative distribution function will have three parts corresponding to x less than 0, x lying between 0 and 20, and x greater than 20 as shown in the diagram. For x greater than 20, the fx will be equal to 1 because total sum of all the probabilities has to be 1 because in that region my fx is not defined. But PDF in this region will always be obviously be 0 as you can see from the diagram above. So fx will be equal to 0 for x less than 0, fx will be equal to 0.05x for x lying between 0 and 20. So let us compute the above problem statement given in the slide in RStudio. Now R doesn't have any inbuilt function for continuous random variables just like we had in discrete structure. So here R basically has the functions for different types of continuous random variables. Now the first statement R norm basically means that will generate random variables which will follow the normal distribution. But for example, we can just try it out and have a better understanding. Now as I run the statement, we can see that x has a vector of random variables which follow the normal distribution. Here, one more thing is very essential for us to understand that the mean and the standard deviation belongs to the standard normal distribution, which is 0 and 1 respectively. That is, we can see negative signs in the vectors as well. Now, if I specify the mu and the sigma, we'll get the result accordingly. Now, the P norm statement basically, or the R norm statement basically has three arguments, the first being x, the second being mean, and the third being standard deviation. Now let us come to the problem statement in the slide. The first question basically asked what is the probability that a current measurement will be less than 10 milliamperes. Here we use the P norm function which will give us the probability. So we have assumed the fact that the distribution follows normal distribution. Now for upper tail my x is greater than 10. So for lower tail, which is the default case, we'll use the P norm function and the argument as 10, the mean being 10 and the standard deviation being 5.77. If we run the statement, the answer is 0.5, which we got in the slide as well. Now the second solution, we found out the probability for x lying between 5 and 20 milliamperes. So basically now we have to use the difference between x lying between less than 20 and x less than 5. If we run the statement, now we got the result as 76%, which is not exactly equal to the percentage which we found out in the slide, because here we have assumed the distribution to be normal, which in fact is not so. But this basically will give you an idea of what are the arguments involved in the distributions which concerning RStudio. Now let us have a look at another example which I'm sure will give you a much deeper insight. The question reads, let a continuous random variable x denote the diameter of the hole drilled in a metal sheet. The target diameter which is to be achieved is 12.5 mm. Due to most random disturbances, there will be inaccuracy. Historical data shows that a distribution of x can be modeled by the PDF given by 20 into e to the power minus 20 into x minus 12.5 for x greater than or equal to 12.5. Now if a part with dia greater than 12.6 mm needs to be scrapped, what is the proportion of those parts? Now here we'll calculate the PDF first. Fx is a function of x instead of a constant value in this problem, unlike the previous question. We need to understand that the part will be scrapped only if the dia is greater than 12.6. Thus the probability of dia greater than 12.6 needs to be calculated, and by using the suitable formula we achieve at 0.135, which is 13.5%. Now this is represented by the colored area in the graph. Now to calculate the proportion of parts between 12.5 and 12.6 mm, we will evaluate the probability for dia lying between 12.5 and 12.6. Using the suitable formula and putting in the constant limits of the interval, we get the answer as 86.5%, also shown in the figure. Now the cumulative distribution function of the random variable x will consist of two parts. The first part being x less than 12.5 and the second part for x greater than or equal to 12.5. Now for the first part, my fx will be 0 since x is not defined here as shown in the diagram. For the second part, we will have to calculate the CDF given by the suitable formula. So after calculating, we get the fx for x greater than or equal to 12.5 as 1 minus e to the power of minus 20 into u minus 12.5. So this particular expression is being represented by this portion of the graph as shown in the figure. Now thus the CDF will enable us to calculate the probability of a dia being less than 12.6 mm. So the probability of the scrapped part can be easily obtained and understood. So here the first part of the question asked what is the probability of the dia being greater than 12.6 mm. So basically it is indicating upper tail calculations. So that's why we will use here 1 minus p norm, because p norm means lower tail. So I have subtracted it from 1 because total sum of probabilities has to be 1. So here I have filled in the arguments where x is equal to 12.6, the mean being 12.55 and the standard deviation being 0.05. The mean and the standard deviation calculations I will show in the next video, but for right now it is important how the arguments are fed in and what is the function of the p-norm function. So if we run the statement, we will get the answer as 15.8%, which is not equal to that in the slide, which was around 13%. Now difference is because here we have assumed that the distribution follows normal distribution. Now the second part of the question asked what proportion needs to be scrapped. That is why we have to find a probability of dia lying between 12.5 and 12.6 mm. So here also we follow the same procedure, and that is how we will run the statements, and it has come to around 68% as opposed to 80% in the slide. The same reason holds true here as well, because here I have assumed the distribution to be normal in nature, whereas we had in the slide we found out that the fx is actually an exponential function. With this, we have come to the end of the first part of our session. So we have discussed in detail the probability distribution function and the cumulative distribution function concerning continuous random variables. In the next part, we will deal with all the parameters, that is mean and variance, followed with continuous uniform distribution in detail. Thank you for watching the video. Please subscribe to our channel for more videos.
Acadgild. Average is dead.